Okay. Good
Good
evening.
Good evening, sir.
evening, sir.
Good evening, everyone. So let's continue with our chapter on postulates of quantum mechanics. Here we go. Okay. We are supposed to complete this chapter today, and then we'll be starting with the last
So
chapter.
total 4 postulates are there in quantum mechanics. 4 or more than that.
I have not kept a count of it. I keep on adding my own postulates even if they don't have any.
Okay.
Okay. So yes, proceeding ahead. But we have learned the original postulate. Apart from that, I have also added some of my own postulates which I feel are going to be necessary throughout the course. Okay. What are basically postulates? Like postulates are just something which need not be proved. Like they exist. It's there. It's fundamental. You need to believe it. It's like somebody would ask me, like tell me that Earth is revolving around sun. Prove it. I'd be like, go outside the Earth and see. I mean, it revolves. So it revolves. Two is greater than one. It's a postulate. It's a postulate. Okay. But some of them we can prove. We want to prove. But the point is, the postulates need not be proved. Like they exist. You need to accept that. Okay. So anyway, proceeding ahead. There's this as well. Which I think has visible annotations. That's all. Okay. So first thing for the day, people we have learned time.
Sir, good evening.
Yes, good evening. Good evening.
Sir, it was by mistake. I did not do it.
Right, it's okay. No problem. No problem. No problem. No problem. So people we have learned time independent Schrodinger equation where h cap psi, the value of h cap into psi, this gives you E psi. So this is an eigen equation. Eigen equation where h cap is a Hamiltonian operator, also known as energy operator. Hamiltonian operator, and we can also call it energy operator. As I said, the JAM admit cards were supposed to come today, but they have not. I think they are postponed it probably. Like you would have got the centers today, but I think so.
Yes, sir.
So h cap is a Hamiltonian operator, also known as energy operator. You apply it on a function, you get the same wave function back, and hence you call it eigen equation. So this is eigen operator, eigen function, eigen value. Now this is energy eigen value. That's fine. Energy eigen value. And what was our Hamiltonian operator? Because we have said it's time independent Schrodinger equation. Hamiltonian operator that we have used was p cap square upon 2m plus v cap, whatever. And then further we have used p cap in this. P cap was minus I h square 2 by 2x, the whole square upon 2m plus v. V cap is nothing but v, just like x cap is nothing but x, y cap is nothing but y, v cap is nothing but v. Okay. And then we get minus square is plus, I square becomes minus h square upon 2m. We get dou square upon dou x square plus v. So this is our Hamiltonian operator. We have learned this. This is time independent Schrodinger equation. Okay. So we substitute it here. So we get h cap, which is minus h square upon 2m, dou square upon dou x square from this one. Okay, first write it, no problem.
So for 3D case, I have
Del square. This dou by dou that will become del.
Okay.
Okay. So we have a minus x square upon 2m, dou square upon dou x square. Okay. Plus v. That's your Hamiltonian operator. Plus v. We apply this on the wave function and we get the energy eigenvalue to the wave function. And we can expand this. So minus x square upon 2m, dou square psi upon dou x square plus v psi is E psi. Popularly, this is how you by heart also time independent Schrodinger equation. Minus x square upon 2m plus dou square psi upon dou x square plus v psi is E psi. However, there is another way in which people refer to by heart, and that is first throw this on RHS. So we have minus x square upon 2m, dou square psi upon dou x square. This is E psi minus v psi. Or I can write E minus v into psi. Okay. Now throw this constant on RHS. Okay. So what do we have? Dou square psi upon dou x square. This is I'm throwing minus x square upon 2m on that side. Okay. So that becomes minus 2m upon x square. What do you have? E minus v psi. And now again throw this on LHS. So we have dou square psi upon dou x square plus 2m upon x square into E minus v psi. This is 0. This is another popular way in which time independent Schrodinger equation is written. Both of them are same thing. Just you have written it differently. Make a note.
So because there is no any function of time, so that is called time independent.
Yes. Nobody is a function of time here.
For the time dependent, there is time involved.
Yes, there will be time involved. So right now psi is here just a function of r. V is also just a function of r. Both
So
of them are
time
just
is an important factor here. So that is time independent and time dependent.
Yes, absolutely.
So please explain in detail. These two things are.
Relax. We'll explore them in detail when we learn applications of Schrodinger equation in detail, and we'll have more.
Done.
Good. Others, let me try it. And tell me.
No, sir, move on. Just
Yes. And people, if the particle was free, then you know what to do. V will be 0. So just mention. For free particle, V would be 0. Just mention it. Because when we learn application, we'll start with free particle problem first. That would be the first problem we will take. V will be 0 for free particle. Okay. Sure. Next. So people, if we want to study time dependent Schrodinger equation, it does not mean it depends only on time. Remember, time dependent means along with position, it also depends on time. Here it is only a position function now. Now it would be a function of position. At the same time, it would be a function of time both. Okay. Similarly, V will be a function of position. At the same time, it will be a function of time both. It can only be a function of time also. That is fine. But it can also be a function of position. So when you say time dependent, it does not mean only time dependent. It means it is additionally, it depends on time. Additionally. Okay. So similarly, Hamiltonian operator, Hamiltonian is always equal to this minus x square upon 2m, dou square upon dou x square for 1d. For 3d, you write del square. That's fine. Okay. Plus v. So this is always correct. However, when you're studying time dependent, you can also write h cap as minus I h square dou by dou d. This is how we can also write this Hamiltonian operator minus I h square dou by dou d. But this you will use only for time dependent Schrodinger equation. Otherwise, you will always use this. Make note.
So please repeat. Just repeat the last part.
Nothing. So basically, Hamiltonian operator is always equal to this. We know this. Just that when we are studying time dependent, basically when wave function is a function of time also, what we will say is Hamiltonian is also equal to this. It is also equal to
So the total term, instead of that, you can write minus I h square del
this.
into.
You can write this also, you can write this also. Both of them are correct.
Okay.
Okay. So for example, when you write h cap psi, this way you can write h cap psi is equal to h cap psi. I mean, x can be written as x, doesn't matter. But the point is, on one side you can use position operator, like the original operator. On the one side you can use this time operator. That's it. So because now it's a function of time also, I will go with the time operator also. So minus h square upon 2m dou square upon dou x square plus v into psi. This is, here you can use the time operator. Minus I h square dou by dou t into psi. Actually, I just need to confirm whether minus exists or not. I have small doubt. Minus doesn't exist. Right. It is this minus. Minus exists only for momentum, not for this. There we have minus. Minus I square dou by dou x. Here we don't have minus.
Sir, dou square by dou x square.
That's right. Okay. There is a minus sign. Make a correction, no minus sign. Okay. So now if you open the brackets, what do we have? Minus h square upon 2m dou square psi upon dou x square plus v psi. This is I h square dou psi by dou t. This is known as time dependent Schrodinger equation. That's it. TDSE. Time dependent Schrodinger equation. It does not mean that it only depends on, like I said. It means along with position, it also depends on time. If there is a partial derivative term involved, it also depends on time. Okay. Along with position, now it also depends on time.
previous slide once.
Sure.
So sir, h cap का definition don't time dependence में position dependence में दोनों same ही है.
हाँ, same ही है. Like this is always valid. This thing is always valid. Just like when it is time dependent, this is additionally valid.
We couldn't write that term for time independent.
Yes, never. Because even if you write, you will get zero otherwise, because psi is not dependent on time and it's partial derivative. So yes.
Oh, yes. Okay.
Right now it's a function of position as well as time. So like here, if you write position as well as time, dou by dou x also exists, dou by dou t also exists. Here both exist. It's a function of position and time both. This you cannot use for time independent plus. Tell me if there is any confusion. It's okay. Clear, people?
Yes, sir.
So one thing, there we got h cap psi equals to e psi, that is the eigenvalue. For here, what is the eigenvalue?
You can write e psi. You will, but now the value of e will change. You can write e psi, but now the value of e will be different. No problem. You write e dash psi, whatever.
Okay.
And sir, ये जो h cap psi equal to h cap psi इसका क्या मतलब समझ नहीं आया, क्या करना चाहते हो?
Nothing. It's like just writing x equals to x, y equals to y, doesn't matter. So the point is,
Okay.
So I'm just writing h cap psi is h cap psi. But one time I'm applying position operator, one time I'm applying the time operator. Both of which will give me the same result. Clear? Any questions, anyone? It's okay. Whatever hesitations you have, you can ask right now.
Yes, sir, we are ready.
Good. And I've already told you, we just pass through the theory whenever we are learning the theory. As far as we understand the numeric perspective, we are on the correct path. Okay. Sure. So that was one thing. Next, there's another additional thing I want you to note. Time evolution of expectation value. Time evolution of expectation value. Not necessarily, I don't think it's required for exam, but for test, you can especially make a note of this. In exam, we will have a constant expectation value usually, but just in case the expectation value varies with time, the average value, if it varies with time, then there's a direct formula of it. The derivative of the expectation value, okay, with respect to time, it is simply given by 1 upon I h squared into the average value of this commutator, a cap h cap. Average value of this commutator plus dou a cap by 2t, partial derivative of a cap with respect to time. This is how the expectation value of operator can be found if operator varies with time, if observable varies with time. Okay. Now, let's understand the conditions, like especially for exam, what we want to understand is, in exam, people, whatever problems you have, expectation value will remain constant. So what are the conditions in which it remains constant by the way? So that's what we can discover now. So for this expectation value to remain constant, what is derivative of a constant? 0, right? So d by dt of this a cap, that should be 0. So under what condition this will become 0? RHS should be 0, correct? So when you say RHS is 0, how can you write that in English? How can you describe it? What happens so that RHS will become 0? Observing this, it should commute with Hamiltonian operator. That's what you can say. Operator must commute with Hamiltonian operator. Commutator is 0, but with whom? With Hamiltonian. No? So operator must commute. Operator must commute with Hamiltonian operator. That's first thing. So that the commutator becomes 0 with Hamiltonian operator. Okay. It means the value of this commutator of a cap h cap, that should become 0. That's first thing. And second, obviously, operator should be independent of time. Not constant, independent of time. It's partial.
Yes,
Independent of time. That's it. Doesn't matter. It could depend on anything, not constant. It can be x, it can be y, it can be z, but it should be independent of time. Not constant. A cap must be independent of time. If it's constant, then it's anyway 0. Derivative of constant anyway here becomes 0 itself. Okay. A cap must be independent of time. That's it. So that this condition, these two conditions, expectation value can remain constant.
Expectation value of that
Observable corresponding to that operator. Yes.
So expectation value is the average value, right?
As well, yes.
So there is no difference at all, no? Between the two names. Expectation
No,
value.
nothing. Expectation is average.
Okay.
So that was one additional thing. Covered up. Next. And before we start with the next chapter, I think I want to ask, like, have you learned polymatrices in matrices chapter?
Yes, sir.
Exclusively, you have learned it.
No. I haven't.
So you did not attend the maths class. Like, why? So I'm asking.
I mean, it was
Sir,
I
the
was
question
introduced. The question, Abbas.
So there was a question.
Yeah.
Okay. But exclusively, you have not learned polymatrices. That's what you're saying.
Yes, sir. Yes, sir.
Okay. So we'll learn polys because polymatrices are important for quantum. Chalo. Done, people. So this is the last topic that I want to teach in this chapter, polymatrices, and related to that, we'll take a couple of examples also. Here we go. Please give me polymatrices. Okay. So different books use different notations. We will use sigma 1, sigma 2, and sigma 3. However, some books also use sigma x, sigma y, and sigma z. It's one and the same thing. Doesn't matter. But order is important. Sigma 1 or sigma x, that's 0, 1, 1, 0. Okay. Sigma 2 or sigma y, that's 0, minus I, and 0. And sigma 3 or sigma z, that's 1, 0, 0, minus 1. Obviously, for a while, you might be also thinking, since when you have learned Pauli's matrices, so why are these so significant? Like, why these three? Like, what is so important about them that, we have three such specific matrices which we learn exclusively? I will try to explain that to you. What is so special about them? But you have to remember them in order. That's important. 0, 1, 1, 0, 0, minus I, 0, and 1, 0, 0, minus 1. So first important property, all are 2 cross 2. That's quite evident. All are 2 cross 2. 2 rows, 2 columns. Second, people calculate the determinant of any of them. Determinant of sigma 1, that's 0, minus 1, that's minus 1. Determinant of sigma 2, that's 0 plus I square, which is minus 1. Determinant of sigma 3, that's minus 1, minus 0, that's minus 1. Determinant of each of them is minus 1. Each of them. Determinant of each is minus 1. Number 3. What about a trace? Trace means sum of diagonal elements.
0.
Each of them. Each of them. Okay. Sum of diagonal elements. That's as we see 0 plus 0, 0 plus 0. 1 minus 1, that's also 0. It's 0 for each. Sum of diagonal elements. 0, 0, 0, 0, 0, 1 minus 1 is also 0. Done?
Yes, sir.
Next. Number 4. All are Hermitian. If you don't believe, we can always check. What is the definition of a Hermitian matrix, people? That A should be equal to
Dagger is equal to A.
yes, A dagger. When you say dagger, dagger basically means conjugate of transpose or transpose of conjugate. How will you write it? All of them must be equal. Okay. So let's check. Let's start with the first one. For example, sigma 1. Sigma 1 is 0, 1, 1, 0. Okay. Let's calculate the transpose of this. Sigma 1 transpose. That's 0, 1 and 1, 0. Let's calculate the conjugate of this now. Conjugate. It's real. Doesn't change. 0, 1, 1, 0. As you clearly see, this is equal to original. So you can say that sigma dagger, sigma 1 dagger is equal to sigma. Okay. Similarly, check for sigma 2. Sigma 2 is 0 minus I 0. Okay. Let's calculate the transpose. Sigma 2 transpose. So that's 0 minus I. Row becomes column. This row now becomes column. Similarly, row will become column. This I0 that becomes column I0. Okay. Let's calculate the conjugate of this. So conjugate of 0 is 0. Conjugate of I is minus I. Conjugate of minus I is I. Conjugate of 0 is 0. Outstanding. As we see, this is sigma 2 dagger now. Conjugate of transpose. And this is nothing but the original matrix 0 minus I 0. Dagger is equal to sigma 2. This is Hermitian. Absolutely Hermitian. Similarly, you can check for sigma 3 also. All are Hermitian. All. By the way, transpose of conjugate is also known as tranjugate. Like this is an official word. Tranjugate. Like this is the meaning of transpose of conjugate. Dagger basically.
Yes, sir.
Done everyone? Let me know if anybody's writing.
Yes, sir.
Yes, sir, as in done or writing.
Done.
Okay, next. Number 5. All are unitary. What is unitary matrix, people?
A dagger is equal to identity.
Yes, A into A dagger is identity. You were about to say A into A transpose was identity, but what is this, if you remember?
Orthogonal.
Orthogonal. A into A dagger is I. This is orthogonal in matrices. Right. But when A into A dagger.
Sir, what is the actual, sir? I reading from A dagger is equal to identity.
That's also fine. Doesn't matter.
Sir,
What does it matter?
No, for
A dagger or A into A dagger. It's fine.
okay, sir.
All of them. All of them. It doesn't matter. Okay. It means dagger is the inverse basically. Like when you say A into A inverse is I now, it means that the dagger itself is the inverse. Or you can say A is the inverse of A dagger, you can say A dagger is the inverse of A. Either way it's correct. Okay. You can just write A dagger is the inverse of A. Is the inverse of A. This is right for each. Okay. So that we can check. Let's take the complicated one. I'll take the B one directly. So what is A, people? A was 0, minus I, and 0. Okay. So basically sigma 2. This was our sigma 2. Now sigma 2 dagger, actually it's the same thing because it's Hermitian also. So sigma 2 dagger is also the same thing. 0 minus I 0. 0 minus I 0. And now we are saying that the product of it should be identity. Let's check sigma 2 into sigma 2 dagger. Okay. So 0 minus I 0. 0 minus I 0. Okay. Let's go calculate. So what do we have? 0 into 0 is 0. Minus I into I, that's minus I squared. 0 into minus I, that's 0. Minus I into 0, that's 0. I into 0, that's 0. 0 into I, that's 0. I into minus I, that's minus I squared. 0 into 0, that's 0. What do we get? I squared is minus 1. Minus minus plus 0. 0. I squared is minus 1. Minus minus plus 1. We got identity matrix. This will be valid for each of them. All are unitary. Done, people?
Yes, sir.
Okay, next. Number 6. All are involuntary. Do you know what is an involuntary matrix?
A square equal to I.
Yes, A square is I. When you say A square is I, again understand the physical meaning of this. It means A into A is I, but we know that A to A inverse should be I.
Equals to inverse, yes.
It means matrix is its own inverse. A is nothing but A inverse. They are telling us A and inverse are same. It means matrix is its own inverse. Matrix is its own inverse, which we already know. Because we have already two conditions. We already have proved that A is A dagger, and we have already proved that A into A dagger is I. So we already have that A into A is I. So we already have that A square is I. For each of them. For each of them, sigma 1 is sigma 1 dagger. Sigma 1 sigma 1 dagger is I. This was our property number or Hermitian. This was property 4. Okay, this was property 4. Hermitian. Property number 5. You involuntary. So if you combine 4 and 5, you are getting 6 automatically. Sorry, property 5 which is unitary. If you combine Hermitian and unitary, you get involuntary automatically. You can write in fact shortcut Hermitian plus unitary. By default, you get involuntary. because A is A dagger, A into A dagger is I. Similarly, A is I. So this just wants me to create a question here. Can you tell me what kind of a matrix plus orthogonal will give me involuntary? Think. Just like Hermitian and unitary is giving me involuntary, something plus orthogonal should give me involuntary. I hope you are understanding the question. A is A dagger, this is Hermitian. Okay. A into A dagger is I, this is unitary. So I just replace A dagger with A because A dagger is equal to A. So A into A is I, A square is I, this is involuntary. So as we understood, Hermitian plus unitary gives me involuntary. So very similarly, I'm just asking. Natural question, okay? It just came right away. What plus orthogonal should be involuntary?
Identity matrix.
Mm-hmm.
So plus or into?
I think plus as into only. I'm just giving you an idea that if a matrix is Hermitian as well as unitary, it is involuntary. So that's the statement basically. If a matrix is dash along with orthogonal, it becomes involuntary. It's English, not mathematics, right?
The orthogonal of its own matrix.
Hermitian and unitary makes it involuntary. Are they symmetric now? Symmetric plus orthogonal. What is the meaning of symmetric?
A dash equal
Transpose
to
is equal to
A is A transpose. What is orthogonal?
A
A transpose A is equal to
equal to
So A transpose can replace
Yes,
A.
sir,
ना
yes,
यार. Yeah,
yes,
sir,
it
yes,
becomes
sir.
involuntary.
Santo.
Okay, so symmetric plus orthogonal. Symmetric and orthogonality that will make it involuntary. Nice way to remember things. Huh? Symmetric plus orthogonal makes it involuntary. This is symmetric and this is orthogonal. Now this is involuntary. Okay, this is not a part of polymatrices right now, but just additional stuff. Anyway, so polymatrices are involuntary. Okay. Next, number 7. Okay, I hope you copied it, all of this. Tell me if you want me to repeat anything. It's completely fine. Next, number 7. All have same eigenvalues. No? See, every property was understood, but like having this property also, this makes it more important for quantum. Like we have 3 different operators, such that if we apply them on a function, we will always get the same eigenvalue. That's interesting. We can any day check. So we can start for one. Let's start with, let's say, the first one. What is the first one? I personally have not had it 0, 1, 1, 0. So that's sigma 1. Okay, so let's calculate sigma 1 minus lambda into pi. So that's 0, 1, 1, 0 minus lambda into pi, which is 1, 0, 0, 1. So this becomes 0, 1, 1, 0 minus lambda flows inside lambda 0, 0, lambda. Let's calculate sigma 1 minus lambda I, which is 0 minus lambda, that's minus lambda, 1 minus 0, that's 1, 1 minus 0, that's 1, 0 minus lambda, that's minus lambda. Okay, that's sigma 1 minus lambda I, that's how you start. Step 1. Second step, you equate this with 0, determinant of this. You equate the determinant of this with 0. So let's calculate determinant minus lambda 1, 1 minus lambda, this is 0. Okay, let's calculate. So this is lambda square minus 1, which is 0. It means lambda square is 1. It means lambda is plus or minus 1. Everybody should have now same eigenvalue. That's what they are claiming. Obviously, doing polymatrices must be something special, that we have so many things coming up together for each of them. Lambda is plus or minus 1. Check for second.
It is same for all.
Same, no? It will be same for all people. Okay? You can check for second and third later. It will be same for all. Nice. And you know,
More properties or not, sir?
Pardon?
Are there more properties or not?
there are, you can create as many properties as you want, but now I'm not going to pen down beyond this. So that's what I was about
So
to say.
these all quite given by scientist Pauling.
Yes. Basically, he just found out some matrices and started finding everything of, related to each of them. And he gave so many properties that were similar. He initially shortlisted many matrices, not only these 2. So there were, I think, 5, 6 matrices he first made. Like, obviously, see, he started from here. If you're thinking, so why only minus I? Why not I minus I? So there were some properties where I minus I were not fitting. There were some properties where I minus I were not fitting. There were some properties where minus 1 and 1 were not fitting. There were some properties where 1 and 1 and this were not fitting. So he started with many matrices. And then he shortlisted these 3 and he said that all the properties I'm mentioning are being obeyed by only these 3 matrices. Okay. So I was about to say that people, you can always go to the Wikipedia page for these matrices. There is a property section. There are 30, 40 properties, and you can always go through them all. But these are the significant ones which I wanted you to remember. But there are as many properties as you want to learn. Like the relationship between them also. You know, like sigma 1 into sigma 2, it gives you something related to sigma 3. Sigma 2, sigma 3 gives you something related to sigma 1. Then you know, sum of square of all, like sigma 1 square plus sigma 2 square plus sigma 3 square. That is also something nice. So all such weird properties are available on internet. Just go to the Wikipedia page. Just search for these matrices on Wikipedia only, nowhere else, and just read the properties there. Okay. Only in your free time, not required. We learned all the significant ones which we want to discuss. Okay. Other properties you need not by heart. Tell me one thing. Suppose in JAM I have given a question. Which of the following properties are correct for Pauling matrices? There are 4 options A, B, C, D. It's an MSQ. It does not mean you need to by heart the properties. So we can verify the properties. If they are saying that all are involuntary, how much time did it take for us to check whether they're involuntary? Hardly 2 minutes or 1.5 minutes. So if at all they give you 4 properties, you have the capacity, you have the ability to believe that you will be able to verify those properties. You don't need to by heart. Till that I have not by hearted all the properties. Just believe in yourself and you will be able to understand and derive that these are the properties that are correct. Don't by heart unnecessarily, don't stress yourself by heart unnecessarily. But provided you know the basic terms, matrices ka terms is important. So you need to go through a good book, maybe HK Das or whatever of mathematics, where you find all the definitions, like involuntary matrix, scalar matrix, square matrix, rectangular matrix, whatever, this and that, upper triangular, lower triangular. So by heart all the definitions of matrices, that is important. Apart from that, you will be able to check the properties by yourself. Okay, so let's continue. So those were the things related to this. Now I want to take a question significant for us right now. So question would be, find normalized eigenvector. Normalization is related to quantum, remember. Find normalized eigenvector of sigma x corresponding to its positive eigenvalue. See, in matrices, they ask you to find eigenvector. In quantum mechanics, they will ask you to find normalized eigenvector. That is the major difference in mathematics. Okay, so you already know how to find eigenvectors, how to find the normalization. You are already aware of the condition, but still we will learn. So to start with, so for example, what is sigma x? 0, 1, 1, 0. And eigenvalues of all of them are plus or minus 1 that we just discovered, plus or minus 1. So they are talking about positive eigenvalue. So which one I will take? Lambda 1 is plus 1. I'm going with this. Lambda is plus 1. Clearly mentioned. Okay. So this is our task. So what is the eigen equation, people? Eigen equation is Ax is lambda x. A's operator. A's operator. Here the operator is sigma x. So sigma x into x. This is lambda into x. I hope you agree. This is eigen equation. Okay. Copy this much. I need to go to the next page. Your operator, matrix operator is sigma x.
Yes, sir.
So let's solve further.
So
What
for
is sigma?
sigma 1, that is sigma x,
Yes.
sigma 2, that is sigma y.
Yes, and
So
sigma
why
p,
is
sigma z.
x, y, z, there is any importance behind them? Or
No such importance. No such importance. It's just the way we denote things. So, for example, if in optics, also, if you have ever wondered that if you were ever confused that that object distance is u and image distance is v, and object height is h1 and image height is h2, if you were because you write magnification as h2 upon h1, many times it happens to students they get confused who was u, who was v, who was h1, who was h2. It's simple. Who comes first? Give it the first letter. Who comes first? Object or image? Obviously, object. First you have object and then you have image. So in letters also, who comes first? You or me? Q comes first and then comes v. In numbers also, who comes first? 1 comes first and 2 comes second. So object u 1, image v 2. You'll never get confused. Okay. So here also 1, 2, 3 x, y, z identity. 1 is x, 2 is y, 3 is z. You don't have to think hard on this. Okay.
No, so just asking. There is any.
No, but the point is, I'm also telling you that in exam also, the best way to remember is
Yes,
1 is x, 2 is y, 3 is z. Okay, next. So let's solve this further. So what do we have? Sigma x, which is 0, 1, 1, 0. Let's apply this on capital X. So capital X, we can write, let's say x1 and x2, or x or y, whatever you want to use. It's a column vector. Capital X is always a column vector. People, variables x, y, z, x, y, x1, x2. If you're thinking about quantum mechanics, what kind of variables are there? People, upspin and downspin. In quantum, one is upspin, other is downspin. It all comes later, like when you will learn, the spins in detail. But this is where the Pauli matrices can be connected. Okay, it's connected to the spins. So if you want, just for like a good feeling of having a quantum idea, instead of writing x1, x2, you can write up and down spin also. Doesn't matter. Okay, anything. So let's write up and down, whatever. Okay. So this is equal to what do we have? Lambda into again x. You can write x, y, x1, x2. You can write upspin and downspin also. Okay. Now, so all we have to do after this is lambda is what, by the way? Lambda is 1. Lambda is plus 1. I think you may not be that comfortable with upspin downspin right now, so it depends. You have to cross multiply. So 0 into lambda, 0 into upspin plus 1 into downspin. That's the first term. Similarly, 1 into upspin plus 0 into downspin. That's second term. And inside, so this is 1 into upspin and this is 1 into downspin. Okay. So this will be equal to. Okay, listen. Even I'm not enjoying this. We'll substitute up and down later. Okay. Let's write x and y. Hang on, what did I do?
No, it's okay. We are comfortable.
I'm not comfortable. Okay, wait. Because we'll be equating also on both the sides now. And doing equating x1 equals to x2, that is where the complications will increase. So wait. We'll just resubstitute up and down at the very end, not now. Sorry. So this is equal to lambda into x1, x2. Lambda is 1 and then x1, x2. I'm going with x1, x2. Okay. Now let's multiply. So we have 0 into x1, that's 0, 1 into x2, that's x2, 1 into x1 is x1, 0 into x2 is 0. Okay. This is equal to 1 into x1, that's x1, 1 into x2, that's x2. So we have our x2 upon x1. This is equal to we have our x1 and x2. Equate numerators, like equate the terms. So first term is giving you x2, x1, and the second term is giving you x1, x2. I have already told you people in the last classes also that you'll never get specific solutions in eigenvectors. You'll always get generalized solution such that one equation will be repeated. As you see, you have a repetitive equation. X1 is x2 is z. So you have to say let suppose x2 is n. Suppose. So what will happen to x1? X1 will also become n because x1 and x1 are same now. X1 and x2 are same. So x1 will also become n. The point is, any value of n which satisfies this equation is always correct. So there are infinitely many eigenvectors. That is what you can see. Okay. So what's the eigenvector? Eigenvector which was x1, x2. You can write it as n and n. And now you can take n common. You'll be left with 1 and 1. I'll be left with 1 and 1 if I take n common. Okay. So 1 and 1 is your linearly independent eigenvector, and there are infinite linearly dependent eigenvectors which are left with n into 1 and 1. You can say the linearly independent eigenvector is 1, 1. All the other eigenvectors, like you can write x, n, whatever, will be n into 1, 1. These are infinitely many linearly dependent eigenvectors. Okay. Copy. But this is still not normalized. This is how you do in matrices. In matrices, you will end up saying eigenvector is 1, 1. You take n common, whatever you are left with, you say that's your eigenvector.
Sir, 1 by root 2 आ जाएगा normalized.
Perfect. Normalize if you want to do so, you have to just basically multiply the row vector with column vector, or you can just write it the other way around. I'll explain. Yeah. So basically, we have got our eigenvector which is n into 1, 1. Okay. So the thing is, in quantum, how do we write this? We write it as n into like upspin. N into, like I said, this one is upspin, this one is downspin. So this becomes, further you can write this as n into upspin like this plus n into downspin like this. Or you can also use phi 1, phi 2. You can write n into phi 1 and you can say n into phi 2. Or just like in matrices you write, you can write nx1 plus nx2, whatever. Okay. So right now, I think we will go with this one. Let's say we have got n1 now. So I will prefer to write phi 1. Hang on, let me think. How do I need to make this right? X star x. This is 2 rows and 1 column. And I can multiply this with 1 row and 2 column. Okay. So either we can go with row column multiplication, or we can use the quantum idea of psi is 1. Hang on. Okay. So multiple ways in which we can write this. One is x vector, which is n into 1 I cap plus 1 j cap. This is how you can write. Another way in which we can write this is the wave function psi, which is n into 1 into phi 1 and 1 into phi 2. 1 into phi 2. Okay. Another way in which we can write this is psi is, like I said, n into 1 into upspin plus 1 into downspin. So my preferred method would be this B1 people. I'm going with the B1. Okay.
So
this
can
is
you repeat the B?
No, it's nothing. Basically, just instead of giving I cap and J cap, you are giving what we used to call it, two bases, orthonormal bases. I and J are orthonormal bases. I dot I is 1 and then I dot J is 0. So very similar.
Not adding them. You're not adding them, no?
No, there is plus. There is plus. I did not write plus. Obviously, there is plus. ठीक है? I've just replaced I cap with phi1 and J cap with phi2, and I've replaced phi1 with upspin and phi2 with downspin. However we can write it, however we want. So this is our comfort zone, people. In quantum, this one in Jam's syllabus, this is our comfort zone. So the point is, what is the normalization condition? The value of psi should be 1. That's it now. So first write the bra vector of this. So bra vector would be n into, you can write phi1 plus phi2. Okay, and remember these are orthonormal pieces, just like I cap and J cap. Phi1, phi2 are also orthonormal pieces. Upspin and downspin are also orthonormal. All of them are I cap, J cap, then phi1, phi2. Okay, then upspin, downspin, all are orthonormal. Okay, are orthonormal. You know the meaning of orthonormal. So like I dot I will be 1, phi1 dot phi1 will be 1, up dot up will be 1. Samjha? I dot J would be 0, phi1 dot phi2 will be 0, up dot down would be 0. Upspin and downspin. If you combine them, no spin, upspin and downspin. If you combine them, no spin. Okay. So up and down would be 0. Likewise, we can create pattern. But anyway, so psi is 1. So let's substitute what do we have? N into phi1 plus phi2. This is the bra vector side multiplied with the ket vector. Multiplied with the ket vector. So this is n into multiplied with the ket vector. N into I've got phi1 plus phi2. This is 1. I hope you are going to tell me something. I just multiply the bra vector with the ket vector. But phi1 will multiply, phi1 phi2 will be 0, phi2 phi1 will be 0, phi2 phi2 will multiply. N into n is n square, by the way. N into n is n square. Now phi1 phi1 is 1, phi1 phi2 is 0, phi2 phi1 is 0, phi2 phi2 is 1. This is 1. What do we have? N square into 2 is 1. What do we have? N square is 1 upon 2. Or I can say n is plus minus under root of 1 by root 2. That's the value of n. That's the value of n. Let's say we can directly write, you have written this much, you can have directly written C1 square plus C2 square is 1. That's the condition now, another way around. Or C1 star C1 plus C2 star C2, that's 1. So here the first constant is n, the second constant is also n. Okay. It's C1 phi1 plus C2 phi2. That's n phi1 plus n phi2. Directly that also you can instead of doing this much.
Yes, sir.
Okay. So the same method 2 would be, you can also write psi, which is n into phi1 plus phi2. You can expand this. So this is n phi1 plus n phi2. So this is similar to C1 phi1 plus C2 phi2. And what is the condition of normalization? Eventually we end up getting C1 square plus C2 square, that is 1. C1 square, C2 square, C2 square, that is 1. Or if complex is involved, then C1 star C2, okay? Then C2 star C2, if complex is involved. Okay. So right now you just have n. So n square plus n square, that will be 1. 2n square is 1. Again, you're getting the same thing. N square is 1 upon 2. Or you can say n is plus or minus 1 upon 2. Anyway, so what's a normalized eigenvector? You found out, people. The normalized eigenvector is equal to capital X, which was n into 1, 1. That is the general matrices, people, that you write. You write n, 1, 1. This you say that this is your linearly independent eigenvector. But if you want to find a normalized eigenvector, you want to find the value of n, which you found out, plus or minus 1 upon 2. So these are our normalized eigenvector, people. I hope it's clear. Tell me if not. And similarly, you can find 5 more normalized eigenvectors. Why 5 more? This is eigenvector corresponding to positive value of sigma x. Similarly, eigenvector corresponding to negative value of sigma x. Similarly, eigenvector corresponding to positive value of sigma y, negative value of sigma y. That way you can find total. In total, we have got 6 eigenvectors. Any questions? Anyone? Anywhere? Please ask.
सर कंजुगेट होगा तो उसमें क्या होगा थोड़ा बताएंगे फिर से.
हाँ, so basically if you have something like this, suppose if I have got psi is 2i phi1, okay, plus 3 phi2, suppose, okay, just a second. I have written the constants. I have put C1, C2. How can I give them values directly? Just a bit. So I can say, let's say we had written n phi1. Okay, so suppose if I'm giving you ni phi1 plus n phi2. Okay, so you can compare. This is C1 phi1 plus C2 phi2. So C1 is actually ni and C2 is n. So now you cannot use C1 square plus C2 square is 1 because you have conjugate. So instead of writing C1 square, you will write C1 star C1. Instead of writing C2 square, you can write C2 star C2 plus. This is 1. So what is C1 star? That's ni star. And what is C1? That's ni. What is C2 star? That's n star. What is C2? That's n. This is 1. N is a normal number. Don't worry about it. So n star, that's n. I star. With ni star, that becomes what is minus n. Ni star is minus ni into ni. This is real. Okay. So this is n into n. This is 1. So what do we have? Basically, this ni becomes minus n. Nothing else changes. And then you have n square minus n square. I into I, which is I square plus n square. This is 1. I square is minus 1. So n square plus n square is 1. You get 2n square is 1.
Same आएगा.
Same आएगा. But if you would have squared, you know what would have happened? If you would have squared, see what would happen? Just directly square the people.
0 वाले.
0 and 0 get 0 equals to 1. Pathetic. If you get ni square plus n square equals to 1, you get 0 equals to 1. So, and hence conjugating becomes important. Understood?
Yes sir. Yes sir. Thank you sir.
Others also, please ask me. I hope you understood this also, this area. It's not that significant, but main is how to find normalized eigenvector. Main is that. Okay. These notations you will become more comfortable with during your masters. It's not significant at all right now. Okay. So this you will get more comfortable later. But I hope you just understood how to find a normalized eigenvector. That's important. Clear, people? Chalo. Next. Proceeding ahead. Okay, I can take another question in the same lines. This was actually one of the just paper actually. I don't know the year. So phi was 1 upon root 2, 1 upon root 2. And they had mentioned that this is the wave function of an electron. Theory was written, and further they had just asked, find the probability of finding the state in downspin. Finding the state in downspin. Okay, that was the question. Find the probability of finding the state in downspin. Okay. So
1 by, what is that? V.
1 by root 2, 1 by root 2.
Okay.
1 by root 2, 1 by root 2. Okay. So I can write this as phi is, you can take 1 upon root 2 common. I'll be left with 1, 1. So how can we write the wave function? 1 upon root 2 upspin plus 1 upon root 2 downspin. Okay. They're asking us find the probability of finding the state in downspin. So people, this is like C1 upspin, C1 psi1, and C2 psi2. Is this normalized or not? First of all, C1 square plus C2 square. It will be normalized. No? So 1 upon root 2 square plus 1 upon root 2 square, which will give me 1 by 2 plus 1 by 2. This is 1. So this is normalized. For normalized, you already know the probability formula directly equal probability that I will have second wave function, or probability that I will have second energy, or probability that I will have downspin. That's just C2 square, if you remember. It was just Cn square. Probability of having En energy or probability of having psi and wave function, okay, that was Cn square upon C1 square plus C2 square dot 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 dot. But if denominator is 1, if the function is normalized, then it was just Cn square. No? This is when it is normalized. Okay, and this is when it is not normalized. In fact, in this we had also learned actually that constants must be real. If it is not real, then you already know instead of writing square, you have to write star and 1. Like Cn square can be written as Cn star. So that's also there. Okay? So that's it. No? Answer is just C2 square. So what is C2 1 upon root 2? No? 1 upon root 2 square probability is nothing but half. Okay? Not this will never be asked in exam, but only because we learned normalization. I thought I will also teach you this just in case you're lucky enough that they ask you this in this. So you get 1 mark, or I think 2 marks, whatever, 3 marks, whatever marks we have. So that's it.
सर C2 में डाउन स्पिन होगा या अप स्पिन होगा?
Down.
ओके
कोई नहीं. ठीक है. Okay. चलो. With this we complete the chapter people of our postulates of quantum mechanics.
So 1 minute wait. That's it.
हाँ, sure. I'm filling out sending you now because the date is only 4th Jan and they're starting with the last chapter. And I've already taken Sunday double lecture. I'll be taking double lecture on Sunday. So nice. Before, like I thought I would give you just 1 month, and I was worried that if I would have to give you a month less than that, or I would have to compromise on the quality. But no. In fact, we'll be completed way before 13th Jan. We should be done by 10th, 11th Jan probably. Let's see. Not way before, a couple of days before. Okay. Done? Shall we?
Yes, sir.
Okay. So let me now just change the slide. Give me a minute. I'll create a new slide. So 1, 2, 3, 4, 4th Jan, and lecture 19B. Done. Sure. Share the screen. Here we go. So the last chapter of quantum mechanics, but this will be a long chapter, people. Okay, because we have to learn a lot of things in this, like step potential, Baron potential, then 1D, 2D, 3D box, harmonic oscillators, hydrogen atom. But it will be fun. This is the most important chapter of quantum that we have, and the most scoring ones. From this chapter alone, again, just like the first chapter SCTQ, a lot many questions will be asked. It can be from 6 marks to 10 marks from this alone chapter. Okay, so something which I was before I was so much scared about quantum. I know now before you were, but now we are not. Now we are looking forward to learn this excitingly. So I received all. See, one of the best parts that I feel in the testimonials you guys have written. Literally, almost all of you have spoken about how well the quantum mechanics journey has been of you. So I feel nice because quantum has been a subject which, if I'm teaching it correctly, it means I'm doing definitely nice in my life. So okay, so all of you almost have mentioned how quantum is going. So I feel good about it. Proceeding ahead, so please give heading to the last chapter. Applications of Schrodinger equation. Okay, today's lecture is going to be again very fundamental. We're not solving any step potential, any barrier, any 1D, nothing. We'll just learn theorems and again the language which I want to use in those topics, people. So just build the ABCD required to learn this chapter. Let's start with theorems. Please give heading. Okay. First, just write with me. Derivative of wave function with respect to position d psi by dx is always continuous, but when hang on, is always continuous as far as the potential energy is finite. As far as the potential energy is finite. Okay, that's important. Potential energy means V of x people. Okay. So it doesn't matter people as a habit. Will you write this? D psi by dx is always continuous as far as potential energy is finite. This means V of x.
Position. Derivative with respect to the position.
Position, yes. D psi by dx, or derivative of wave function with respect to position. That is always continuous as far as potential energy is finite. But remember, I have not mentioned whether the potential energy is continuous or discontinuous. Potential energy could also be discontinuous. Now, what if there is a sudden jump, like step potential? Initially it was 0, and suddenly there is some value. Here the potential energy is discontinuous. That's fine. Potential energy can be continuous, it can be discontinuous, doesn't matter. Write it. However, potential energy could be continuous or discontinuous. Doesn't matter. Continuous or discontinuous. Okay. So, for example, if suppose you have a potential energy like this, let's say initially it was increasing and then it is decreasing. Suppose this is V of x. So here potential energy is continuous. It was increasing and then it is decreasing. Sudden turn, sharp turn, but still continuous. No? They are still joined here. Okay. So here it is continuous. At the same time, it should be finite. It should not be infinite. So potential energy is not infinite. Right? It's finite. It is starting from some value. It is ending at some value. Potential energy starting from some value. It is going to 0. It is still going to 0 is also finite. It's not infinite. People. So this here you can write V of x is continuous and finite both. Continuous and finite. Okay. Since potential energy is finite, that is important. D psi by dx is continuous. And what is the meaning of this? There are two regions, left region and right region. At this point P, derivative of the wave function on the left side will be equal to derivative of the wave function on the right side. Derivative of the wave function on the boundary of the left side will be equal to derivative of the wave function, okay, on the right side. This happens only at the boundary, at P, at point P. At point P. That is the meaning of continuous. It means it doesn't change. And like from here to here, whatever was the derivative here, same derivative exists here. Discontinuity would mean that the values are different, Continuity means that at this point values are same. So if you have a different wave function on left side, if you have a different wave function on right side, doesn't matter. It doesn't matter because at the boundary it will remain continuous. Discontinuity would mean that the values are different, Continuity means that at this point values are same. So if you have a different wave function on left side, if you have a different wave function on right side, doesn't matter. It doesn't matter because at the boundary it will remain continuous. For example, like in gravitation, we learned, let's say like inside the gravitational field formula, that was 4 by 3 pi r rho g, Okay, and outside the formula was gm upon r square. Doesn't matter. At boundary, both of them are going to give you the same result, and that was gm upon capital R square. At boundary, both will give you the same value. That is a meaning of continuity. At boundary, both has to give you the same value, even if inside you have a different value, even if outside you have a different value. So even if you have a different function on left, even if you have a different function on right, at point P, they have to give you the same value. So that is the meaning of continuity, first of all. Clear this much? Next. So I'll
comments on.
take your time. So you can take this as case A in this. It's finite and continuous. Remember, if the position may become infinite, doesn't matter. Potential energy is still becoming zero. It's not infinite. If you're thinking, sir, if I keep on going like this, it goes until infinity. But position is going to infinity. Potential energy is going to zero, so it's finite. It's not infinite. Infinite would be something like this, where it goes way into the sky. That's infinite.
Yes, sir.
Next, similarly, if suppose I would have given you something like this. Okay, let's say this is x-axis position. Let's say this is your v of x. Okay, so and they have mentioned that on the and let's say this is zero. So on the left half, potential energy was zero. On the right half, potential energy is suddenly constant. Let's say v equals to 5, here v is 0. So what do we see, people? Potential energy is discontinuous now. V of x is discontinuous. Doesn't matter. We don't care about the discontinuity of it. Is it finite on left side? Is it finite on right side? Yes, it is 0 now. Yes, it is finite. It is finite. It is finite. So since it is finite, again, derivative of wave function on left side has to be equal to the derivative of the wave function on the right side at the boundary. It should be equal to derivative of the wave function on the right side at x equals to 0. At x equals to 0 at this boundary. Derivative will be continuous. So potential energy continuous or discontinuous doesn't matter. Derivative will remain continuous. I'm just trying to make you understand the meaning of English of this, because students read this continuous, discontinuous, they'll be like, okay, go out. Okay. They're just trying to understand what it means. Derivative of the wave, because these are the things that we use during our derivations.
So boundary is any point of discontinuity in Vx, or it can be any point.
No, this is x equals to 0 anyway. At all the points x is 0. V of x is changed. X is still 0 at all the points. This is why x is not.
Okay.
Boundary is the position coordinate. So at all the points x is 0. V of x is changing, we don't care. You can write it's y-axis, along y-axis. Along y-axis. Here, people. So here also, I wrote point P, but actually you don't need to write point P. You just write at x equals to 0 here also. Because if this is 0, if this is something else, then something else. If this is 5, then 5. It's basically the position coordinate. Right? Correct. So don't write point P, write at x equals to 0. Or x equals to 3, 5, whatever point this is, we don't care. But at that point, it will remain continuous. Clear? Okay. But if suppose, like, if you take a 1D box problem, people, where you may have learned the potential energy is 0 in between, and then all of a sudden it becomes infinite. Infinite. Here also all of a sudden it becomes infinite. In that case, we don't have a boundary condition. You cannot say derivative is continuous here. So suppose this is origin. Just suppose this is origin. Okay. And let's say for a 1D box, let me, because we're learning a pattern, I'll teach you that pattern only. Let's say this is v of x. Okay. So from 0 to suddenly it is going to infinity. So now x equals not continuous. Now wave function is not continuous because v of x is infinite. V of x is infinite at x equals to 0. Okay. Wave function is not continuous. d psi by dx is not continuous. So here you cannot apply. You cannot say the derivative of wave function on the left side will be equal to derivative of wave function on the right side. You cannot say that. Clear?
So just one last question. जो बोल रहे हो कि इनफाइनाइट नहीं रखता पोटेंशियल, वो थ्रू आउट द डोमेन ऑफ द एक्स है या फिर लोकल डोमेन ऑफ द एक्स, जहां पर मैं इंटरेस्टेड हूं. मतलब अगर मैं एक्स और नेगेटिव की तरफ लेके जा रहा हूं तो पोटेंशियल 0 है, इट्स फाइनाइट. सो वहां पे डेरिवेटिव ऑफ वेव फंक्शन इज डिफाइंड, राइट?
हाँ, here it is defined. The definition is not the problem. Wave function will exist here because wave will be there. But the point is, there is no continuity of the wave function now. We are only talking about not continuous. We are not saying that wave function doesn't exist. Wave function left exists.
मेरा मतलब ये था कि d psi by dx is continuous on the left
पूरे left में is continuous. पूरे left में. But basically we are talking about boundaries, boundary conditions we are speaking about. Okay, so here I have a boundary now. Like here I had a boundary. Where here I had a boundary. So where potential changes, boundary means what? Where potential changes suddenly now. So from here potential changes its nature. Here potential changes its nature. Here potential changes its nature. So we're trying to learn the boundary conditions. So at this boundary now d psi by dx is not continuous. Okay. We are just basically the whole first theorem is all about boundary conditions. How do we derive that? How do we understand that? Clear? Chalo. Others also please ask me questions. Don't hesitate. So that was the first thing. Second. So if you are thinking, but sir, then what happens to wave function? Wave function vanishes. If potential is infinity, wave function cannot exist on that side. That's it. That's the second theorem. If potential is infinity, wave function vanishes. You don't even say 0. It doesn't exist. Don't even say it's 0. Just say it vanishes. It doesn't exist. Doesn't exist. Vanishes. Okay. And this one I try to explain you also. Like for example, we had that a e raised to x, and I told you if x tends to infinity, wave function becomes infinite. That's not possible. It means it doesn't even exist. Right? If something like this we learned before, I'm just trying to give you another small glimpse of this. If x tends to infinity, what happens to this? A e raised to infinity. No? So this is a into infinity. So this becomes infinity. So here the wave function becomes infinity. That's not possible. It means this has to vanish. A has to become 0. You can say this doesn't exist at all. Simple. Okay. So v of x is infinity, psi of x vanishes completely. Next. Third. If there are more than one linearly independent wave function belonging to the same energy eigenvalue, then the energy is said to be, you should know the word, then the energy is said to be, do you know what is the energy called? If there are more than one linearly independent wave function belonging to the same energy eigenvalue, basically multiple energies share the same eigenvalue, then energy is called noise. I did not hear. Degenerated. Energy is called degenerated. You may have come across this word. Okay. So what is the meaning of this mathematically, physically, whatever? So people, when you apply operator, suppose A, if you apply it on a wave function, okay, then you get some eigenvalue. Suppose you are getting eigenvalue, let's say small, psi1. Now, if there are more than one linearly independent wave functions, So you have got, let's say, psi2, but psi2 and psi1 has no relation. I mean, it's obvious. If psi2 had a relationship, if you would have said that psi2 is 3 times psi1, then it's cheating. Then you will write that, obviously you will end up getting a. You can throw 3 outside a psi1, you will have a as a factor. So we cannot say that it's linearly dependent. It should be linearly independent. So if psi1 and psi2 has no relation whatsoever, even after that, if you get the same energy eigenvalue, then you can say that energy is said to be what? Degenerated. This A is known as degenerate value. 2 energy is known as degenerate value. And how many degeneracies are there? For example, right now 2. So in that case, you can say energy is twofold degenerate. Energy is twofold degenerate. But interestingly, psi1 and psi2 should be independent now, because obviously they are dependent and it's cheating. In that case, we will keep on getting energy eigenvalue infinite times. Psi1 and psi2 are independent wave functions, and still they have the same energy eigenvalue. So if there are n eigenfunctions, people, n wave functions sharing same eigenvalue, then energy is known as n-fold degenerate. Okay, you can write if there are n wave functions sharing same eigenvalue, energy is called n-fold degenerate. N-fold degenerate. So for example, something like this. Let's say E1 cap, sorry, energy operator, E cap into psi, H cap, sorry. H cap into psi1 is giving you, suppose, some energy E0 into psi1. But when you apply H cap on psi2, you are again getting E0, psi2. When you apply H cap on psi3, you're again getting E0 and psi3. And similarly, you have got H cap into psi n, you're again getting E0 and psi n. So there are n such wave functions. All of them are sharing the same eigenvalue E0. Okay, all of them are sharing the same eigenvalue E0 here. You can say energy is n-fold degenerate. Any questions, anyone?
Done, sir.
And if you're thinking where exactly you can apply this, well, for example, people in hydrogen atoms, recalling, what was the energy value? Something like n square, pi square, h square. No, sorry, no, n square was in the denominator there. So do you have the formula? Pi m noise. All I could hear is noise. Okay, so maybe like minus 13.6 upon n square. I'll go with this. Leave the whole expression. Leave it. Again, there is just only noise, but okay. Your voice is breaking. Your voice is completely breaking. Leave it. So this was energy back then. We can write z also, that's fine. I'm avoiding z right now. Suppose z is 1. I just want to teach you something. So the point is this n square that we write. Just say, if suppose n square is allowed to be written as nx square plus ny square. Suppose if n square is allowed to be written as nx square by ny square, then I want to ask, what are the possible values of nx comma ny? What are the possible values of nx comma ny such that I get n is 1?
0, 1, 1, 0.
0, 1, and 1. Now, you cannot use fractions. Nx and ny are only integers. Nx comma ny are only positive integers. Okay, 0 are positive integers. So you can just write nx comma ny, they must be greater than or equal to 0. So 1 is 0 1 combination, other is 1 0 combination. So if you add 0 square plus 1 square, you get 1. If you add 1 square plus 0 square, you still get 1. But either way, you're getting 1 now. Is there energy getting affected? Tell me in any of this case. Even if I get 0 1, is my energy getting affected? No, minus 13.6. Even if I add 1 0, is my energy getting affected? No, it will be still minus 13.6. So the point is, there are two wave functions. Where one wave function will have 0 1 nx and y quantum numbers. Another wave function will have 1 0 nx and y quantum numbers. But both of them are sharing same energy equal. So here you can say it's twofold degenerate. So I'm just trying to explain you the meaning of degeneracy. However, we'll be learning this in detail later. Okay. So you can just write if you want this. We'll be learning them. But still trying to make you understand what is the meaning of degeneracy. Energy is not getting affected. Even if you write 0 1, even if you write 1 0, energy remains minus 13.6. So you can say E equals to minus 13.6. In this case, is twofold degenerate. In this case, you can write E equals to minus 13.6 electron volt is twofold degenerate. Twofold degenerate. People, one-fold degeneracy means non-degenerate. One-fold degeneracy would mean non-degenerate. Simple. Write it above margin. One-fold degenerate means non-degenerate. It means it's unique. Nobody can share its value. Nobody can share its value. Unique. Write down one-fold degenerate means non-degenerate, and it also means unique. Okay. Next, number 4. Any linear combinations of degenerate wave functions. Any linear combination of degenerate wave functions is also an eigenfunction. Is also an eigenfunction belonging to same eigenvalue. Belonging to same eigenvalue. I'll explain this. I always love to learn things mathematically when they give this in English. They don't do everything, they just write the theory, they don't do these things, but we can understand this mathematically. Any linear combination of degenerate wave functions is also an eigenfunction belonging to same eigenvalue. Okay. Let's learn this. This will be the last topic for today because obviously it's going to be your time also. But anyway, so let's take any two degenerate wave functions. First of all, let psi1 and psi2 be the two degenerate wave functions. I'm trying to make you understand the meaning of the definition. Okay, so when you say two degenerate wave functions, it means what? They will share the same eigenvalue. Simple. They must share same energy eigenvalue. They must share same energy eigenvalue. So let's say that energy eigenvalue is E0. Suppose E0. But let's say I want to be the two degenerate wave function. They must share same energy eigenvalue. Let's say it is E0. So how do you write the equation now? What is the meaning of it? It means when you apply Hamiltonian operator on psi1, you will get E0 psi1. And when you apply Hamiltonian operator on psi2, you will still get E0 psi1. This is the meaning of degeneracy. E0 psi2, sorry. This is the meaning of degeneracy. Or both of them are giving you the same eigenvalue. Okay. But now what is the question? Any linear combination of these degenerate wave functions will give me same eigenvalue. Okay, let's define now. Let's define a random wave function. For example, suppose f is suppose some alpha psi 1 plus some beta psi 2. F is linear combination of the two wave functions. Huh? Linear combinations of two degenerate wave functions. Two degenerate wave functions. Let's just like linear combination of psi 1 psi 2. Okay. So let's apply Hamiltonian operator on H cap F. Okay. What are we getting? H cap into alpha psi 1 plus beta psi 2. Okay. Let's throw alpha outside. H cap psi 1. Let's throw beta outside. H cap psi 2. Okay. But what is H cap psi 2? That's E naught psi 2 already. What is H cap psi 2? That's E naught psi 2 already. Huh? Let's take E naught common people. If you take E naught common, what are you left with again? Alpha psi 1 plus beta psi 2. But who is alpha psi 1 plus beta psi 2? That's F people. What did you get? H cap F is E naught F. F is also sharing the same eigenvalue. F is also sharing the same eigenvalue. So if we have two degenerate wave functions, technically you will have infinite degenerate wave functions. Anybody and everybody who can be, you can write this as 1, 1, you can write this as 2, 5, you can write this as 3, 7, you can write 5, 10. You can have infinite wave functions now sharing the same eigenvalue, but we don't care about this infinite. Psi 1 and psi 2 are linearly independent, but others are linearly dependent on them. Huh? So when you talk about degenerate wave functions, you're strictly talking about these two psi 1 and psi 2, which are not dependent on each other. Psi 1 and psi 2 are independent people. They are linearly independent because all the others will be linearly dependent on them. They will be linear combination of them. So in exam, a very good question can be asked, which has never been asked. I would love to ask a question: is that how many degenerate eigenvalues are there if degenerate wave functions are there? If let's say I would have given you if energy is 2 fully degenerate. Many students would mark 2. 2 fully degenerate means 2 wave functions. Huh? Technically, because there are infinite wave functions. There are 2 linearly independent wave functions. That's important to understand. Okay, we can now have infinite such combinations, but there are only 2 linearly independent. So if they ask wave functions, answer is infinite. If they ask linearly independent wave functions, answer is 2. Thank you so much, people. You are ready. We'll meet tomorrow. Please revise these 4 things and come. Only noise. Thank you, sir. No problem.
Thank you, sir.
No problem.
Thanks, sir.
No problem. Shall I end session, people? Let me make a brief writing. Later.